Greetings and welcome to Making Stuff with Chris DeHut. In today's video we're going to take a look at a rather unique keypad that we use on microcontrollers. Now this particular device is different than the common ones such as this that we've done in our digital keypad video, which will be linked down below. It's different in that it is, this one we're doing today is using analog output, and we're going to read that analog output with an analog to digital converter that's built into the Raspberry Pi PICO. Now the great advantage to that is simply input savings. Now this style here, this is a 16 key keypad digital. It requires 8 GPIO pins to interpret all those key presses. The one we're working with today, which is right here on our workbench, only requires one GPIO signal, 3.3 volts and ground. So you greatly minimize the number of pins utilized from your Raspberry Pi, and that saves them for other parts of your project. Now, one of the things that really fascinated me with this particular one, besides being about the only one I can still find, is the removable keycaps so that you can put your own legends on them. And I'm going to put that back together right now so I don't lose that. But you'll see the button goes on to the base switch, and then you've got a clear lens that goes over the top of that where you can put a legend in between. This is a project, it's a resistor calculator and a regular calculator. It was a kit that I think I bought off of AliExpress. I did one with my grandson. Had a lot of fun making it, but really like the key styles. And with this type of key legend, you can kind of get very creative way beyond 16 key inputs by using a mode select switch within your keys to get more functions out of each key. So for today, what we're really going to focus on is simply how to get one of these working. Now I do have a link down below for a source of this, and it's in China. However, I didn't buy this particular unit from them. I bought this unit probably 10, maybe 15 years ago when I was tinkering on another project. So it's an older unit, and I'm sure I bought it locally. However, you'll probably find them on AliExpress or even the source that I linked down below in the description. To get started, we'll take a look at a Fritzing diagram of how it's wired up, and it is truly very simple. The keypad itself, this isn't an exact model of it, but it's close, a close one that I could find in the Fritzing library. We have 3 pins on it. They are labeled, in my case, VCC, that would be your power supply, ground, and then the output signal, and that would go back to the Raspberry Pi. So to make the connections, we are taking from pin 36, our 3.3 volt output signal, and bringing that into VCC. We are connecting the Raspberry Pi PICO ground signal to the ground of the keypad, and then the output of the keypad to the, let me get that to pop up here, pull that down. Pin 31, which is GP26, and it's the analog to digital converter channel number 0. Now, if you don't know how to find this, there are these diagrams in the Getting Started with the PICO manual that I highly recommend you get. You can also download this diagram from a number of different sources. But what you gain from this diagram is a way to find what pin does what. And in our case, we're using pin number 31, which is GP, General Purpose Pin 26, and it is our analog to digital converter number 0. On the Raspberry Pi PICO, you've got 4 analog to digital converters on it. Number 4 is strictly for an internal purpose, for an onboard sensor, but analogs 0, 1, and 2 are available for you to use on your projects. For this presentation, I'm providing you with two Micropython programs that we can use to set up and work with this analog keypad. And the first one that we're going to work with is, I'm calling it a key val utility. And what that will allow us to do is to extract the analog value for each key press. Now, because it's analog, you're not going to get a perfect value for every time you press the key press. If the voltage in varies a little bit, your voltage out will vary. So you need to establish ranges between each of the keys. And this utility program will help you to create the keypad that I'm showing here. Or I'm sorry, the key map. And you're going to find that just having it run idle, you'll get an average reading of some amount. It's actually changed because I developed this example probably a month ago and probably used a different Raspberry Pi and a different power supply. So my numbers are a little bit different than they are here today, but nonetheless, this will work for our example. But what we want to do is run this program and then press each key and then record its value that we're getting from it. And then from that, we can establish a range for that key based on these values. Now, the range will go from 0 to 65,535, a full resolution at 16 bits. Now, there is granularity to this because, in truth, the RP2040, the microcontroller that's on the Pico, is only 12-bit resolution. So what Micropython is doing is just extrapolating that out so that that 12-bit resolution fits into a 16-bit resolution output, which is common amongst a lot of modern microcontrollers. So we're going to be working with 0 to 655.35 as our range. We're going to import the machine library that gets us access to the hardware of the Pico, and in this case our analog to digital converter number 0, and we're just simply going to call that keypad. And then we're going to set a variable called raw to 0 as a base measurement variable. And for some reason I've got it there twice, so I'm going to delete this. And we should be good to go further into the program. I'm also importing a Micropython version of the time library, and we're also going to be using threading, but not necessarily in this particular program. That's for the next phase of this. And I'm just saying that this is simple code to find the average value for each key to obtain the key code values, which are here. And this table will be used to write the next program. We're going to set up average value variable and then a pointer, and that pointer will be used in this loop down below. So to demonstrate it, first let's get it running. I'll click run. I'm all programmed and have everything on it. And you'll see my average value just sitting idle is 270 to 280 range. Okay? And then up in my comments up here, the last time I had this set up a month or so ago, it was at 408. Again, I could have a different power supply. A number of different things may have changed since that time. But we're going to enter a loop here, and we see that running. It just simply says raws, we're going to set that to 0. And then while pointer is less than or equal to 19, we're going to set the variable raw to a keypad read value. We're going to read the ADC channel and get its value. And we'll give it a brief sleep, and then we're going to index the pointer. And what we're doing here is taking an average of 19 readings with this particular button. Then we'll set our pointer back to 0. We'll say the average is equal to the raw divided by 20. Technically 20, 0 to 19. And then we'll print that average. and then we'll reset average, and then we'll sleep a tenth of a second, and then repeat. And you'll do this. This will run continuously, but as we'll see here, I'm going to hold down what will eventually be button number 1. Now I'm holding that down for a while, and I want to get several readings, and you'll see it stabilizes. It went from 58.9 to 655. And this is the running average that we're seeing here. And each time it does this sample, it takes 20 samples to give us that one singular reading. So my number 1 key is going to be 655.35. And that'd be nice and close in the range that we're seeing here. If I go to the next key, which would be key number 2, the way I'm going to map it, it'll go to 58.820, we would say, and so on. And we would record all these values into here. And this would give us key number 1, our average value that we see down below, number 2, number 3, and so on. And then there's a value in between, and this is calculated as the halfway point between key number 2 and key number 1. So we just find that halfway point, and these will be our dividing lines when we decide whether a key is a number 1 or a number 2 range. If it's greater than this amount, it's probably number 1. When it's less than this amount, it's probably number 2, and so on. And that's how we create our key map. As I alluded to in our previous key-val utility program, we're going to map this keyboard the same as our digital keyboard that we presented in the other video. So 1, 2, 3, A across the top, and then asterisk, 0, pound, and D at the bottom. For the actual program example that you would probably be utilizing, we've structured it such that we're putting the work of reading the analog signal in a thread. And that way we're utilizing more capability of the PICO, which is dual core. It's got 2 cores, so this thread in theory is running in that other core and not taking up valuable processing time for our main loop. So we'll see how this all looks in code. Near the top, we've got our comments to explain the operation of the program, where to connect the wires, and then our key map that we developed with our key-val utility program. We're importing the same libraries. I've also turned on an LED on the Raspberry Pi PICO, and that, of course, is this little blinking LED right here. And that's just to show you that things are running in our main loop. We're going to create our keypad using machine.adc and channel number 0 as noted here. And we're going to establish a variable called raw and set that to 0. We're going to establish 2 more variables, last key and user key, and set those to null. And those are to help with getting rid of key bounce or automatic key repeating, which can be a big problem to deal with, not only in digital circuits, but also, in this case, kind of an analog to digital program system. So that's what these 2 variables are doing, is getting rid of that possibility, greatly getting rid of that possibility of key repeats that we don't want because they will confuse our programs. Now this is the function that's running in the thread, and we're going to come back to that as I describe all of this. I want to first come all the way down to the main loop. Now the main loop starts out just simply toggling the LED, nothing more than for us to see it blink. But we're constantly in our main loop. Every time we come through, we're going to check to see if user key, the variable user key, is not equal to null, meaning it actually has a value in it. If it does, we're going to copy that value into another variable, and we would commonly refer to that as a local variable that we would perform more actions on. And then we're going to set user key back to null. And then that way, our routine up here running in the thread can write new key presses into that variable. And then finally, all I'm doing with it is just simply printing key code equals key code. And right now, I will press button number 3, and we see how that happens. The other thing I want you to pay attention to here, and this is part of that key debouncing that I do in many programs. I'm going to press and hold what will be button number 5. I'm pressing and holding it, but nothing popped up here in our shell area. Once I release, then we'll see the key code value come through in our main loop. And that is a side effect of how I perform key debouncing in my programs. Now this line here is actually what's going to start this function running in a thread. _thread.start new thread. Very simple there. And the routine I'm going to run is analog keyboard scanner. And this simply starts the thread running with this function. Now, we have a global variable, user key, that's the one we're writing to, and we're able to read in our main program and in our main loop. We're going to set last key to null at the very start of the whole program, and then we're going to loop forever using a while true. Now we're going to look. If user key is equal to nothing, then I can do something. If it's not equal to nothing, meaning it already has a key value in it, down here we're going to hold off processing any new key presses until that user key is fetched down below here. And that's how we debounce it. So now we're going to look at the actual ADC value, the analog to digital converted value. That's done with this keypad, read._16, and we'll store that numeric value in the variable raw. We're going to set our key to null just so we've got a clean starting point for our key value. And now we'll look at those values from our analog to digital conversion. If raw is greater than 62305, then it must be key number 1. If we look at our map up here, all the rest of the keys, we need to do a double comparison, and we'll make sure it's within a range around the average value for our key press. So if we're greater than 56177 and less than 62305, meaning less than this, then it's most probably key 2, and so on and so forth, all the way through all our different key maps. And of course, if you're not using the numbers 1 through 0 through 9, and then ABCD, and then the hashtag and asterisk, you would substitute this with the legends that are on your keypad. Finally, we get down to here at the end of this decision-making cycle. And then we're going to say, if key is not equal to null, that means we've got a key, we will set that to last key. And that's the last key pressed, and we're going to store that key in the buffer. And then finally, we will compare against if the key is equal to null, and last key is not equal to null, meaning the key press in buffer and button was released, then we will pass it along by moving last key here into user key, which is what we work on down in our main loop. And then we reset everything so that the buffer is free to accept a new key press. Finally here, we've got a time of a sleep of 20 milliseconds, and that's just to slow the loop down a little bit. And that moderates the behavior of the loop. And if you want to, you can tweak that up or down. If you get too excessive, too long of a delay here, then you could literally miss key presses. So don't get too carried away with that value going up. Going down is probably not going to have much of an ill effect. So again, we'll run that, and I'll just go through all our different key codes. 1, 2, 3, A, 4, 5, 6, B, 7, 8, 9, C, asterisk, 0, hashtag, and D. And that's how you can work with these neat analog keypads. They're very efficient on the use of GP pens. You only really need just one, and you can read 16 different keys. Very, very handy for use in a lot of different applications. And if you let your imagination run a little bit wild, there's an awful lot of projects that you can do with microcontrollers, such as this neat calculator that require the input from keypads. So have fun playing around with this. I am going to provide links below for our digital version of this same keypad, as well as links to videos that we discuss threading, as well as analog to digital converters in a little more detail. I apologize for glossing over it here, but the video gets a little too long and people seem to grump about that. Also, these files are available on our companion website, makingstuffwithchrisdehut.com, and I'll provide a link below in the description so that you can jump right to there and download the Fritzing diagram as well as the source code that we just went through here, just to get you going a little bit quicker. I'd like to say thanks for spending time with me today, and I look forward to seeing you in the next video. If you haven't done so already, please subscribe and give us a like if you enjoyed the video. I would also like to mention that there's going to be 50, 60, perhaps even more videos for the Raspberry Pi PICO series that I'm producing. So with that, I'd like you, if you would like to, you should visit our companion website, which has a listing of all the videos and a detailed description of what they cover for the Raspberry Pi PICO, as well as many of our other videos. Thanks again for watching, and I look forward to seeing you in the next video.